Hello, and good morning, good afternoon, good evening, wherever you are. My name is Michael Weinstock. I'm a Director of Emergent Technologies and Design, and I'm here with Elif and some of our leading students to talk to you about MTech and the year ahead.
And so we are going to show you a couple of slides about the work that we do in MTech.
Maybe you say something about yourself and where you're from.
Yes, I'm Elif, and I'm from Istanbul, Turkey, and I'm a studio master in MTech, and I've been here for 14 years in London, and very happy to be at the AA. So this is us, and in front of our design and build project that we completed. And we have a very structured course in MTech. It's made up of phase 1 and phase 2. In phase 1, you are introduced to certain skills and theoretical background about the work that we do, such as bootcamp, design and technology, biomimetics, emergence, and all that knowledge that you gain during phase 1, you use that basically in phase 2 to develop your thesis dissertations.
Okay, so in phase 1 we have a number of elements. These are taught, and we ask you to start again from scratch. All of you know something, some things you know really well and some less well, but we start with boot camp, which everyone is reworking and rethinking, and we're making objects and artifacts. We have 2 seminar series. The first one is natural systems and biomimetics, where we look at social insects, and particularly we look at their behavior to produce algorithms, and these are the ones you're seeing now, worked on agent-based systems, and then we use those systems to develop forms and structures and processes. We have a lot of people who come in and interact with us. That's Mike Cook, a very famous engineer leading Borough Happold. And we introduce you, get you to work with a lot of computational analytical processes.
Hey everyone, my name is Milad. I'm a PhD candidate in MTech, but my research is situated within the MTech broader agenda. We dealing with the complex systems and complex problems, so we deal with solution sets rather than the single objective and multiple objectives. We use genetic algorithm, evolutionary computation, and we use statistical analysis in order to address those problems, and we further publish. We have collaborative works with the master students, and it's like all collective research agenda that MTech is trying to pursue and pushing forward.
Typically in these things we're evolving urban tissues. We start with breeding from tissues that we've studied in evolved cities such as Fez, ancient cities, Barcelona, and some very contemporary ones. And we explore huge sets of variable outcomes, and we learn how to select from those for different criteria and different behavior.
One of our studio courses, Design 1, in this course we develop material systems, complex material systems, and we work with different types of geometries, different computational methods, and there's always feedback between the computational world and the physical world, and all of our computational experiments are calibrated from physical experiments basically. So
you don't have to move that fast, that's kind of speeded up video.
And like I said, we work with different material systems, as in this case it was concrete. We look at the dynamics of these materials, how they perform in certain contexts, and by learning that information we translate it into our physical prototypes and models, and all of these prototypes have some kind of performative behavior in relation to different types of environmental external factors. We are also very much interested in working with robotics and how robotics can perform, again, with different criteria. As in this case, you can see how self-shading analysis can serve as a toolpath for robots. We also work with sheet panels, as in this case metal, We've been working with curd folding and robotic incremental sheet forming in the past year, and really looking into how to synthesize different, let's say, fabrication systems for certain performance-related criteria.
So Design 2 is getting near to the end of the talk part of the course, and we send you out into the marshes, mainly because most of our work is situated in extreme environments. We think this is what the world is going to have to deal with. And you bring together in this final design phase all of the techniques and technologies that you've learned to make a proposal for a productive system, in this case in the marshes, that over the course of the next 50 years will go from slightly damp to under 2 meters of water. The kinds of techniques that you've become very familiar with and tested in other things are put to work, first of all, in modeling the projection of climate and ecology on this particular peninsula. And this is one of the examples from one group of students for a dispersed system, up to 40,000 people living there, where we're able to produce real tested data for the performance both of the buildings, the mariculture, and the behavior of people in these kind of new environments, which we need for the future. Okay, this is kind of really interesting stuff. We've recently, in the last 2 or 3 years, just been exploring. This is from one of our early attempts working with VR, but we're working both with AR and VR in this is a real housing estate with really distressing social problems, and it's a collective design from all the inhabitants. So we're interested to enable new kinds of participatory work. The same for new forms of construction. One of the issues with complex forms of constructions is how much data is embedded in the object. We're moving away from plans, and we've been exploring using iPhones and other materials to coordinate the placement of complex geometry components. Design and build's always been part of our culture. We do it because we love it. It's not assessed. Everybody has a role. And we've had a long history in the AA of building, sometimes we think quite elaborate structures, sometimes very simple. This was done in Switzerland. You can see how large it is. ETH is in Zurich. We have collaborations with many universities around the world. This was built for the Timber Expo in Birmingham, widely seen by all architects across the UK. This was the previous year, also built at full scale. We moved during the year from early models to full-scale building. We've been exploring last year a very new technology. Elif has taken the lead on because of her knowledge and love of robotics. I think she loves to dance with robots. And we've been bringing together our knowledge from curve folding and sheet metal forming into this new technology. So this is our very first. We're going to continue with this, but you can see how we developed both the form, its behavior, and the techniques for forming and changing the shapes of flat sheet metal into these complex curvatures.
We developed custom joints for this project, as you can see, made with 3D printing, and then we fill them with resin. It's a very collaborative process. All students take part in it, and they all have different tasks. And they're all very interested, obviously, in making things, building things, because we learn from building. And by doing these experiments, in a way, we learn to fail better, so that next time we run them, we already have gained the knowledge and experience. And it's a really exciting, fun kind of
I don't know why I'm going crazy there. I've forgotten what happened was.
The assembly process was quite exciting. You will see it very soon when we went on site, basically, and assembled it all throughout the day. It wasn't this fast again, it's fast forward, but it was quite. We learned a lot from it, right? Yes. And was quite nice, and it stayed there throughout our end of year show, so that the public could visit it as well. And this video has recently been accepted to Robots in Architecture 2018 conference for the video call. So, as it was mentioned before, we really do care about publications in conferences, and our students always publish their work after they finish their thesis. We have an amazing fabrication lab. It takes the whole basement of the AA. We have 2 large-scale robots, a lot of 3D printers, you know, anything that you can think of in a fabrication lab. So we have really nice facilities here at the AA London.
But we don't have a lot of money, so we have to be really inventive. And this is an old, very ancient kind of architectural principle. What, as well as the technology, also have to be really creative and inventive. Yes. And that's learning how to talk to robots, learning the behaviors of things, and using those as design inputs rather than making a design and then translating it into a material system. And of course you get to play and develop these things, and you will be, this is what you will inherit in the coming year. This was our very first with curved metal sheet formation, and we're going to be working and exploring this at larger scales and with more components in the next years.
And another important point about these kinds of projects is that we have collaborations with leading practices such as Bura Happold in this case. So the students are also introduced to some of London's, you know, really good practices as well throughout these explorations.
Okay, so phase 2, this is up to you. We have kind of 2 big fields of work. You get to choose who you work with. You develop your own topics, you make your proposal to us, and we discuss with you how to make the proposal, modify it, what the methods are, and then you're off and running. We're going to now see and hear from 2 groups of students about their dissertation work. So,
okay, so I'm Rita, and I'm here with my teammate James, and also our teammate Tim is not here with us. But we're going to present to you our project, which is the biopneumatic structures. So first we start with the context, which was Almeria, also known as Mar de Plástico, because of the 36,000 acres of plastic greenhouses in the area. So most of the fruits and vegetables come from here. And as you can see from the photos, we did both an analysis from going into the site and also an urban analysis, which made us understand the ecological impact of these greenhouses in the area.
Yes, as you can see, the extent of plastic coverage of the entire engineered landscape of the site. So that really shocked us, and also that really drove us to dive deeper into the project.
Yeah, so as you can see, this was one of the analyses that we did of the urban analysis. We also analyzed the crops of the area. We overlaid the information. We really had to be very focused on the information that was needed for this project. So we also analyzed the climatic information, overlaid also with the crops analysis.
Yeah. The biomimetic approach we're taking is really interdisciplinary. So instead of taking a look at the engineered solution, we're looking at the solution already existing in the nature for millions of years. So in this case, we're looking at the natural ventilation system in the biological system. And you can see on the right, the CFD analysis where we adapted, and through iteration, we're able to achieve the optimum section of our shape. And also another important and powerful tool we're using is the evolutionary computation. So with this tool, we're able to populate and generate millions of solutions within a really relative short of time and analyze it in order to achieve a optimum form.
Okay.
As you can see here, with 400 generated solutions, we're able to analyze all of them using the analytical tools we mastered from the previous studio course.
So as you can see, this is one of the CFD analysis that was done on, it was done on most of the individuals. They were grouped so that each group has a representative. So this was the final analysis of the geometry.
Yeah. So studying MTech really gave us the opportunity to master all the analytical tools we require in order to do the digital design. So I think all of these tools are really useful for both future professional practice as well as academia research. As you can see here, we're doing the surface rationalization and also structural performance in order to understand the design, the sequence or the consequence of our design.
And also, it's important to have the necessary research so that you can support the ideas of the design and the analysis that you're doing. And another important factor was also the fabrication of this type of project. So it was a lot about the logistic and assembly of it.
So in the end, as you can see, that's the system proposal integrating the passive cooling system as well as the solar desalination system. So this is really a systematic approach instead of a singular building design approach. As you can see, this is a visualization of our final design proposal.
Mm-hmm. Yes.
And how it's actuating and adapting to different wind conditions.
Yes, and also adapting with the ventilation so that it was able to control the temperature inside of the greenhouse. This is another view from the exterior of the adaptation of the pneumatic structure. And finally...
Yes, so to conclude this presentation, we think well, in my opinion, I think with MTech, we're able to master all the digital design powerful tools, but at the same time, we'll also emphasize the reasoning and the logic behind the design. I think that's makes this program standing out compared to other similar program.
Thanks, James. And I'm also here. My name's Neil. I'm from a small town outside of New York. And my project is actually entitled Infrasonic. So different from what James and Rita focused on, sort of on evolutionary computation and sort of aggregating these big plastic greenhouses. We kind of looked on the material side of things and how we can grow our own material and dedicate it to earthquake-prone settlements. So really our project's ambition is how can we tackle a construction system in Kathmandu, Nepal, and how can we grow a composite material system that we can perhaps build a 4-story building and out of an organic material. So as many of you guys know, in 2015, an earthquake hit in Nepal, and it actually displaced over 6.6 million people. And my group, Abhinav and Miguel, who are not here with us today, but we had a chance to go to Nepal and see the sites. And we talked to the people, and we found that they have a big want to rebuild, but they just don't have the means or the capital to, or the material even, to actually build something that's earthquake resistant. A lot of their construction processes are predated. They have to rebuild a city every 100 years. And so they kind of go back to just rudimentary practices that that obviously don't work, and it becomes expensive over time because they have to keep rebuilding over and over again. And so our goal, what you see on the map here, is most of the buildings in Kathmandu were affected in the heart of the city, and a lot of those buildings were made of adobe construction. And ironically, adobe construction actually contributes to over 80% of the overall pollution in Nepal. And so that's funny because adobe as a material is very high in mass and extremely brittle. So this is why in our research we kind of look at organic materials, looking for something that can be biodegradable, easy to produce from local resources, that is low cost and also can perform similarly to adobe. So in our proposal, we want to use this new biomaterial, which is called mycelium. And so we started growing the mycelium here in MTech, in our studio. And this is what the substrate sort of looks like at day one. We tested different substrates to see if we could increase the strength of our organic material. And how can we make a formwork so that we can build a block or some sort of composite system that would help us build the 3 to 4 story building. Like Elif said earlier, a lot of what we do here at MTech is fail. And this is one of those examples. How did we fail from our experiments? What we learned was that growing our mycelium within a fibrous material system, it actually binds to the mycelium. And so what we found was if we could make a formwork that was made of non-fibrous materials, it would actually build what we needed to do. And what you see here, actually I brought 2 samples in with me today. It's a perfect example of how we learned from those failures, right? So this was a result of using a non-fibrous system as a formwork.
You just like growing mushrooms.
I do like growing mushrooms, actually.
And spawn to grow.
That's important. That's the important part. Like here at MTech, we're really open to explore what we want to do.
Yes.
And I mean, growing mushrooms is a very crazy
Yes.
idea, but as long as you do it systematically and you have how the material can perform and how you can test it properly, that's what we want to see. Okay, so we've built this material. We made this. We made this system. We found that it worked. So how can we computationally do this? So where can we go? What can we learn from our physical experiments to take to our digital experiments, and then vice versa, right? So we do an agent-based form-finding system where we abstracted some of the principles of mycelium growth at the molecular level, and we produce a variety of solutions, just changing just simple parameters such as how these agents can collect in some places or distribute in others. And what we do is we want to test this. So everything at MTech we produce and we test. And so this is an example of a structural analysis that we performed on our 3 to 4 story building proposals. What we learned was actually this branching system that we were able to produce could dissipate energy overall on the global structure. So by creating an open system versus a closed system, we found that an open system actually works a lot better because it dissipates the energy within that one branch, allowing this thing kind of move. And the good thing about the mycelium, bringing it back to the material study, is that its innate resonant property allows for that energy absorption, and so we could be able to dissipate energy a lot faster. So like I said, it's always this loop between digital to physical and back again.
Okay, so what happens to you after MTech? Where do you go? What we're very proud of in MTech is that students who are architects and some who've come in as engineers, there's no difference in where they go. We have many who are working in high-end engineering practices, Borough Happold, but within the culture of London, all the major leading, most famous practices have MTechers in them. There's kind of MTecher family distributed right through London, and especially in their specialist modelling groups, the code groups, and now at Grimshaw and places like that in their material system groups. We really love publications. We want you to do them. I've done a lot myself in the past, but my job now is to encourage you to publish and help you find those opportunities, and we'll be doing that with you. We'll also be encouraging you to put in papers once you finish your work for these kinds of conferences and journals, and we've had many successes with that. And here we are for getting more information. We've had a number of responses for questions. We'd like to very briefly provide answers for in the last few minutes or two that we have.
Perhaps we can also talk a little bit about what you see around us, like the
Yes.
books and some of the models that we could fit in this room behind us.
The books are really important. We still have the culture of the book. So you've seen the visual presentations today, but nobody passes or fails on those. The final output you make are some of these very beautiful books. And these are all available for you from the last 15 years when you come into studio. You can borrow them. We all sit in the same open room. Staff as well. We don't have a separate office. And these are part of the history of MTech and the embedded knowledge in these books that you can start to study, and we explain it to you, and you build on from what their work has done to drive the work forwards.
Yes, we are all taking those books all day. Like they're all just scattered around the studio.
And we like to keep our models in studio as well. So some of them you can see behind all of the different types of interesting models that our students have developed throughout the years. They're also in the studio. So it's a really nice, rich environment. And also we have our PhD by design students sitting in studio as well. So there's a really nice culture between, PhD students, MArch students, MSc students.
We often get asked about what's the difference between doing an MSc or an MArch or a PhD, but actually we all work together. The differences are really just time scale and, of course, cost. It's a little bit one term cheaper to do an MSc than an MArch. There's very little professional difference in the world now, in most countries, but particularly in London. Between an MSc and an MArch. You just get a little longer to think and a little longer to work on a MArch, one term longer. And some people really like that extra time to reflect and to develop their work.
Yes,
We have mixed teams. So, for example, your team.
Yes.
Yeah. We have one Jimmy, the one that is not here, Tim, is MSc.
I think the difference is once the MSc graduates, we are still carrying on the same project, but also exploring new territory within the same domain. I think in that sense, that gave us more time to generate really fruitful research.
Yes.
I think as a PhD student standing in the MTech studio, I found it very fascinating how we collectively grow and we help each other back and forth. I'm learning from these guys, and ideas are floating around. Ideas are floating around, and I sit in the corner and I was looking at them and like, this is very interesting research, and I really like how intertwined and how collectively we're growing as a studio.
I think what we're all trying to say is that MTech is really a family here. I mean, it doesn't matter where you're coming from, who you are. You really come and you enjoy working in the space and love sharing ideas. No matter if you're a PhD student or if you're an MSc student or if you're a tutor. I mean, we're all friends and we're all happy. We're all love to be together.
MTech family.
And I'm still learning, and I still love being there. It's just a pleasure for me to go into studio every day. I wish I could spend more time there. It's your turn.
So there was a question about our research agendas on fabrication and design and build especially. And MTech has a history of working with timber for the past more than 10 years. And then last year we decided to look into kind of other material types as well, but obviously our experience from timber has served a lot in these new experiments. So we started working with metal sheets, and as you saw in the video, we started developing techniques for curved folding and incremental sheet forming with metal. And this year we are going to continue with that experimentation further, and we will be working with sheet metal, but again looking into how to develop complex geometries, double curvature geometries with sheet metal. So for example, we will be exploring metal expansion, again metal forming. There's a huge range of techniques out there, and we like to use robots a lot, and we always like to reinterpret how we can kind of transform, let's say, traditional techniques by using these kinds of new fabrication techniques and the tools that we have, such as robots. And another kind of interesting research agenda that we are developing in MTech is related to additive techniques by using robots. So some of our thesis projects have explored 3D printing with robots, as you saw in some of the videos. And that is also a continuing agenda for us, so we like to develop that further.
And we have a special interest with the robots that a lot of the dissertation projects are exploring how small mobile robots can be used in societies that have extreme climate and ecological difficulties. We reinvent through robotic fabrication the use of materials. We've done work on sand and on salt, and where there are readily available materials in remote places, you can't import any materials. So how do you use those readily available materials and turn them into something like that's useful for construction? And we all find this kind of really fascinating dialogues to engage in. There's one other set of questions that maybe one of the students would like to respond to, is how much knowledge, we often get asked, do you need before you come in, and what kind of softwares do you use?
To answer that question, I would say study at MTech doesn't require any knowledge before you enter in the program, because our very knowledgeable tutor will teach all the tools covering all the domain of our study. And as our research develop in the thesis phase, we'll mainly also develop our own customized interest and software knowledge in different fields. In our case, for example, we want to do more like air, wind related analysis. So in that case, we're doing more research and learning in the CFD platforms. But mainly the tools and software we're using in the studio is heavily based in Grasshopper and Python.
Yes, like me personally, I chose MTech because I really wanted to learn more programs, like more digital things, and I can definitely say that I learned even more programs than I was expected to. Like, I didn't know about genetic algorithms. Like, we also work with robots, the CFD, wind analysis, structural analysis. Like, we really use those tools and we learn them, and like collectively, like everybody in the studio, you can ask anybody, and like between PhD, tutors, even our classmates, we all help each other to understand those tools. So it's really helpful.
Yeah, I think that's the most important. I mean, it's not about the program itself, because those are changing every day. I mean, what is new today was already 10 seconds ago. It's been old. So it's really about learning how to learn, and MTech kind of teaches you the logic and gives you like the base for these things that James and Mira were talking about, and what we've been talking about today. And so it's good. Don't be afraid. It's definitely going to be a great learning curve, but it's a fun one. And
yeah, in the beginning I was afraid. I'm like, how am I going to learn all of those things? And in the end, like, see,
now you're an expert.
Yeah, I hope so.
These guys know more than I do. When you come in, you don't know very much, and what you do know, we ask you to forget. But we try really hard to make you leave with big smiles on your face, really confident about your abilities, that you can be a real architect that can make a significant difference in the world because you've mastered these tools. But as Neil and the others have pointed out, it's not just the tools. You learn a way that you'll always be able to adapt to new tools. And I think that's the most significant thing. Architectural values are permanent, tools are temporary, and they're remade and reinvented by every generation. So I think we're kind of done, and we've covered our what we wanted to say. If you'd like to get in touch, the website will lead you to us, and you can email anytime to Elif or I, and we'll answer. I don't know if the students will, but sometimes, sometimes we can get them to do that. But we're also going to press them pretty hard this time to be working hard. So, but we'd love to hear from you. So, thank you.
Thank you.
Thank you.
Thank you.
Bye.